2018 higher paper for year 10. I'm going to do my best to get this done quickly so it can be in one video. So here's your formula sheet. I'm not going to read any of the question. Describe what is meant by transverse waves. The vibrations of the wave are going to move at right angles or 90 degrees to the direction of the wave or the wave's energy. So many people left out vibrations and you only get 1 mark there. Then you've got to use this formula. Look, V equals 3.13 times the square root of D. Now that is, it throws a lot of people off, but when we come to this one by here, the square root of D is 1.87. To calculate the wave speed, I literally just, it's going to be 3.13 times the square root of D. Well, the square root of D is 1.87, and that comes out, so I've done my calculation there. Look, V equals 3.13 times 1.87, which is my value I just got, and that comes out to be 5.85. This one you need to rearrange. So because the square root of D and 3 times 3 are together, they need to stay together, so V goes up top. And I need to rearrange then, so square root of D equals V over 3.13. So the V in this case, so to get this value is 3.83, and then my square root of D is going to come out to 1.22. And you don't have to do any square root ends because you just leave the value of square root of D. The graph then, oh, hang on, we got one more question. Chris suggests, I'm going to leave that there. Chris suggests that the depth of the water increases 4 times the wave speed doubles. Use data and the table opposite to explain whether or not this statement is true. So if the depth is 1, the speed is 3.13. And when the depth increases 4 times to 4, and I've got all this information from the table here, 6.26. So it is actually doubling, isn't it? 3.13 times 2. So the statement is true, and those figures I got from there. So you can see when the depth was 1, 3.13. When the depth was 4, 6.28. So that's where I got these figures. These are just numeracy questions. And then the graph, people struggle with, because if you don't get this one, if you're not able to work this one out, people just leave the graph. But you're only losing a point. So even if you didn't get this, you could still plot all the remaining ones, and you'd still get 3 marks. So this is what it looks like. It's a nice curve as it goes up. It's not going to be a line of best fit because it doesn't flow correctly. The scale you get marks on. So because my highest value is 7 there and 4 there, I think for 4 marks should be very achievable. And then the last question on here, or last page. So to calculate the wavelength of water when it's got a frequency of 0.2 hertz in a depth of 2. So you've got to go to your graph now. You've got to go for the depth of 2. The wave speed is going to be 4.5. It's told me that my frequency is 0.2. So when I use the equation, wavelength equals wave speed, 4.5 over frequency 0.2, I get 22 meters, 3 marks. Let's not be leaving that one out. Chris now suggests that as depth increases, the wavelength decreases. Explain this. So for a bit more work for 2 marks here. But I've said he's incorrect, because if you increase depth, the wavelength also increases. So it's not an inverse relationship. It's a proportional relationship. So, and I've pulled some information out here just to prove it. So in the table, as depth increases, the speed increases. So there's my formula for wave speed, frequency, and wavelength. So when V equals 4.5, the wavelength equals 22. So let's increase now V to 5 and see what happens with my wavelength. And when I do that, the wavelength also goes up, look. So he's wrong to say that the wavelength decreases because it's actually increasing. So as my wavelength increases, my depth increases. And that's that question there. The diagram shows a common domestic ring main circuit. 2 advantages. Well, I've put many here. Now, these have got to be pretty much like the sentences I've written because they will knock marks off. Cables can be made thinner, so there's 2 paths. Each cable carries less current. Sockets, not plugs. You can't say plugs. You got to say sockets. Can be placed anywhere in the ring. Same voltage everywhere, 230 volts in the ring. And you can have separate switching because you've got those sockets everywhere. State the function of a live wire. It is to carry current at a high voltage, and we can add on to that to the appliance. So the live wire carries it to the appliance, whereas the neutral wire carries it at low voltage away from the appliance. Describe the function of the earth wire. It's to carry current safely to the ground if a fault develops. For 1 mark. For your next mark, give an example. So if a live wire touches the metal case of an appliance. This is a bit of a stinker, because for 2 marks, you've got to say AC is current that continuously or constantly changes direction. You just can't say changes, because it's not changing clothes or changing hairstyle. Changing direction and magnitude for 2 marks. Magnitude there. And then you didn't even need this line. DC is current that flows in one direction. And then this one for 4 marks, because it's 4 marks and it says use equations, S on the end, I'm going to need a 2-step process by here. So it's asking me for resistance. Well, the only resistance I know is the 1 over R plus 1 over R2. It's not going to be that one because there's not enough information. So it needs to be this one by here. There. I mean, I could go and use this one, but I still need to find current because I still haven't got a current. So I know my power. My power is 2,760 watts. I also know a voltage. So the one I'm going to use to find out my current first, so I can use with my resistance, is P equals VI, or PIV, P equals IV. When I rearrange that in a triangle, I put my finger over I is P over V. So I got 2,760 over 230 equals 12 amps. Now I'm going to use this 12 amps now to calculate my resistance. Look. So resistance equals V over I, 230 over 12. I'm going to get 19.6 ohms. You could have done it with the other equation I said, with the I squared. And it comes out the same. You can look at that yourself if you pause the video. Question 3 now. A group of students set up the following circuit. Okay. So SCS, voltage, current, series, parallel. Series current is the same. So series current is the same, and then everything else is opposite. So it adds. So in a series circuit, the voltage adds up. In a parallel circuit, it's the same everywhere. In a parallel circuit, the current adds up. So let's have a look at the first question. Calculate the voltage across R1. So it's not going to be this, because if you think of this and this being 2 separate devices in a series circuit now, so if you condense this, this is going to be 1 voltage and this is going to be another voltage that adds up to 12 volts, because parallel in a series circuit adds up. And I know this looks like a parallel circuit, but it's a parallel circuit within a series circuit. So this whole thing is a series circuit with a parallel in it. So voltage is going to add up. So let's find out my voltage. Well, I know that current in a series circuit is always the same. So it's going to be 2 amps there, 2 amps there, it's going to be 2 amps there, it's going to be 2 amps everywhere, apart from inside this. Okay, so my current there is going to be 2, my resistance is 2. I can use V equals IR to get my voltage to be 4. So that would be 4 volts there. Now, if it's 4 volts there, 4 plus something here is going to give me 12. And that something is 8. So 12 minus 4 is going to be 8. So I've brought my voltage down here for 8, because now I need to calculate the current through each of these. Remember, now this little thing is a parallel circuit. So in a parallel circuit, current adds up. So it's going to be a different current year and a different current year. But the good thing is, voltage stays the same. So it's going to be 8 volts here and 8 volts there. So if I know it's 8 volts there with 12 ohms, and I know it's 8 volts there with 6 ohms, I can now calculate for I. And I've done that. I've rearranged my equation. For R2, it's going to be I equals V over R. I equals 8 over 12, which is 0.6. And then done the same this side. 1.3, and it makes sense now because 1.3 recurring add 0.6 recurring is going to give me 2 amps, and it should be 2 amps. It should all add up to 2 amps because there's 2 amps flowing around this series circuit. So these 2 amps are going to get split through this parallel circuit. 6 marks there. I may have to do this video in 2 sit-ins. We'll have a look now. We're on 10 minutes. Okay, so this one, a lot of information. I got 780 there. He paid for it, and he paid 950 there. But then he paid this and that, and it cost him that, basically. So I've put it in a little table. So before he had these roof, solar roof panels installed, he was paying 780 for electric, and he was paying 950 for gas. Then after, he was paying £830 for electric, so it makes no difference to his electricity bill, but it does make a difference to his gas bill. And it says here, gas was used to heat water in the house in 2015. State other figures allow you to come to this conclusion, because the cost of gas decreased from 950 to 840 in that time. So and we can show that there. It went from 950 to 840. Calculate the expected payback time. So payback time equals cost over saving. Pork turnovers cause sickness. So your overall cost is 4680. You're saving, well, let's see how much we're saving. If it's costing us this there, and then it's costing us this there, it's one minus the other. So I'm saving £110 from 2015 to 2016, whenever I had it installed. So it's going to be the cost over the savings, and that's going to give me 42.5 years. Is the payback time. This one, tough question here. Explain how an increase in the cost of a unit of electricity and a unit of gas would affect payback time. Well, the cost of electricity is not going to affect anything because it's the gas that it's decreasing. We can see from that table up the top. So the unit of cost for electricity would make no difference to payback time. But the unit of cost for gas, the payback time would actually reduce because more money is saved. If you think about this, if it's costing more per unit, and I've got those solar panels doing the job of, so I'm actually saving more. It's cutting down my payback time because if I didn't have those solar panels, I'd have to be paying the increase on that. So it doesn't increase my payback time, it actually reduces it. And then we've got this one for 3 marks then. During the 2 years, the cost of electricity did not change the number of extra units of electricity used in 2016, and it was 300 kilowatts. So that's my energy that I was using. Use an equation from page 2 to calculate the cost of a unit. All right, so we know we've got 300 kilowatt hours. From this equation from page 2, we've got units used, so that's what it's giving me. Then my power, and then my time. It's asking me for time. So it looks like, actually, I'm going to be using this one because it wants to know a cost per unit. It's giving me the units used, and I kind of know my cost as well, don't I? So let's have a look. Where's my marker? So cost equals units, which is that, times my cost per unit. Well, that's what I need to find out. Let's put it in a triangle. So units are tied with cost per unit. Let's stick cost up. I need to find out my cost per unit equals the cost over units. Well, this one's easy because it's giving me in the equation 300. But where did I get 50 from? I got 50 from 830 minus 780. Let's have a look. Electricity. There it is, look. 830 minus the 780. That's what it cost me. How much extra it cost me during that time when the electricity bill went up. So now it's cost me 0.16 pence. Tough question for 3 marks, but doable when you know how.